Okay, so I hope everyone had a nice break. Right? Feeling energized. It's the afternoon. So in this workshop, well, my initial focus was that it was going to be a talk, and then so I checked the checkbox for the workshop, and now it's a workshop. Instead of sort of like in the talk, I would rather go at a surface level of how does multi-party FHE works and sort of just tell you about the applications. But I thought that in the workshop it's a good opportunity to go deep, like dive deeper into the schemes and how does it work internally, and that is what I'm going to do today. So I'm just going to, instead of just talking about multi-party FHE, I'm going to introduce you to the scheme, like how does the scheme work as a developer, how do you think about this, and then I'm going to build two applications using it. The first application is pretty trivial. It's like a simple, how do you match make homomorphically? Like how do you use FHE to make sure that you find people using match make. And the second application is homomorphically running ML inference on private inputs. So you can encrypt someone's input and run ML model on top of it homomorphically. Okay. So this is the link for the Jupyter notebook that I'll be using throughout the workshop. And this Jupyter notebook has everything that I'm going to be sharing today, and then you can sort of use it on your own later. Now, I've divided this workshop into two things. So the first thing is the code thing that I'll be telling you about. And the second thing is a hack and be document. If you're interested in more theoretical aspects of it, like how does it work from number theory point of view, like the hardness assumption and stuff, then you can refer to that hack and be document in future, but I wouldn't be talking much more about the theoretical aspects of it today. But that hack and be document has everything about, you need to know about the theoretical aspects of all these things. Okay, so let's get started. So can I just remove this for a while and let's get started with the Jupyter notebook? Looks good? Okay, this is working cool. Okay, so turns out for the applications that we're building today, you only need ZK11, which is one of the FHE schemes, right? And when I like to think about ZK11 is even generally in FHE as well. When I like to think about FHE, I first like to think about plain text instead of the ciphertext, because every operation on the plain text directly translates every operation on the ciphertext directly translates to the plain text. And for most of the workshop today, we would be directly using the rich structure that the plain text itself gives you. And we'll try to write circuits that make use of the plain text as much as possible, as efficiently as possible, writing the circuit itself as efficiently as possible using the plain text. So, first we'll talk about the plain text of ZK11. Okay, so in ZK11, the plain text is a polynomial in this ring. So what is this ring? This ring is so let's say the ring Rn is R modulus x to the power n plus 1. What this essentially means is that any polynomial, it is a polynomial up till degree n minus 1 with coefficients that are reals. That's it, that's what this ring means. So take any polynomial, any arbitrary polynomial with real coefficients, but with degree less than n minus 1. Right? Okay, so this is what I mean by a plain text in ZK11. So any polynomial that has coefficients as reals and has degree less than n is a polynomial in this ring, right? Sorry? Reals value 1.2.3. How many precision are you talking about? After decimals? It depends. Depending on the computation that you want to do. But it could be. It depends on the parameters that you set. It is dependent on your application. It could be Typically, we set it to 40 to 50 depending on the application. Like we scale the value so that we get precision of 40 to 50 or whatever that is, depending on your preference. Okay. Now, like for example, over here, x by 8 plus 1. This could be a plain text, right? Because it has a degree less than 8, and all the coefficients are in reals, right? Okay. Now, if I give you any arbitrary polynomial, right? Any arbitrary polynomial that exists, you can reduce it to this particular ring by simply observing this particular thing, right? Like because x to the power n in this modulus can be written as -1. Right, because x by n mod x by n plus 1 is -1. So you simply replace x by n with -1, and then you can reduce any polynomial to this ring. So you can find the representation of any polynomial in this ring with this reduction. Okay, any questions? You can just stop me meanwhile whenever there's a question. Okay, so okay. Now this particular polynomial, this particular ring structure has some special property. And we usually refer to that property as negacyclic property of this particular ring. So what do I mean by that? Okay, so let's see. X by n is equal to -1. Does it make sense? Representation of a polynomial that is x by n, when reduced by x by n plus 1, is equal to -1. Sorry, the reason for that is, like, you usually try to do long division, right? X by n plus 1, 1, x by n plus 1, negate it, you cancel it, you get -1 as the remainder. So x by n reduced by x by n plus 1 is -1, right? So any value that is x by n is equivalent to -1. So when you multiply two polynomials in this ring, when you're multiplying, let's say this is a polynomial, a0, these are the coefficients, right? a0, a1, a2, a3, multiplying it with b0, b1, b2, b3. The coefficients would wrap around, because a multiplication of x to the power 0 with x to the power 4, x by 3 would be x by 3. But a multiplication of x by 1 with x by 3 would be x by 4. Right? Powers add up in the exponent. Now you write x by 4 as x by 3 plus 1, and 3 is -1. Right? So when you multiply two particular polynomials, some of the terms wrap around and they become negative, and this gives rise to the negacyclic property of these polynomials when you multiply them. So the terms wrap around and become negative. Over here I've shown an example of what the multiplication would look like when you multiply two polynomials in this particular ring. Okay, so does that make sense? Like, any doubts? Cool. So over here I've written a negacyclic multiplication, like the code for how do you multiply two particular polynomials in this ring, and the concept remains the same. Okay, so we can multiply two polynomials in this ring. So CKK's plain text is a polynomial in this ring. We can multiply when we multiply two polynomials, we get negacyclic multiplication. When we add two polynomials, well, we get normal coefficient addition that you get in any polynomial. When we subtract two polynomials, we get normal addition, normal subtraction that you get with any polynomial. But the special property to remember in this case is that you get this negacyclic nature in multiplication, that the terms wrap around and become negative. Now, if you take a polynomial in this ring and set that as the plain text, let's just I'm just calling that as the plain text of CKKS. So that particular type of encoding is known as coefficient encoding. That you simply take a polynomial in this ring, which is r x by n plus 1 in this ring. You take a polynomial in this ring, and you simply call that, and if you take that as the plain text, this particular thing is known as coefficient encoding. And the reason we call this coefficient encoding is because there's a different type of encoding that we also use in CKKS. So this thing is coefficient encoding, but there's also something called SIMD encoding that exists. In SIMD encoding, the way it works is that so in SIMD encoding, you can encode a vector, like a vector of reals, as a polynomial, so that a multiplication in the polynomial domain acts like element-wise multiplication on the vector. So for example, you have two vectors, A, B, right? These are vector of reals. You've got reals here. There's a way to encode these vectors into polynomials A and B such that polynomial multiplication of these polynomials would result into element-wise multiplication of these two vectors. Okay? This is SIMD encoding. And what I mean by SIMD is like single instruction multiple data, right? So the normal computer architecture word that you're familiar with. So this is known as SIMD encoding. And the reason why SIMD encoding works is, if you're familiar with FFTs, you're familiar with the convolution that exists in FFTs, it just leverages that property to do this. If I have to dive deeper into that, like if you're curious, I can dive deeper into that. But like that would be a diversion for the talk. So I've written an explanation in this hack document of how it works, like it works internally. But as a developer, you just need to know that when you use SIMD encoding, a multiplication of the polynomial results into element-wise multiplication of the slots. As simple as that. Okay, and addition and subtraction follows. It's element-wise addition and element-wise subtraction. Okay, sounds good. So now we know two encodings. We've got coefficient encoding. That is a simple plain text, like a ring, polynomial in this ring. And now we know SIMD encoding, right? So, which is like you can perform element-wise multiplication and element-wise addition and subtraction. Now, sorry.
Just a tiny question about the digits behind the zeros you mentioned, right? Because when you say you work with 40, 50 behind zero, now if you multiply two reals, you add to the digits. How do you deal with that?
Yeah, you get to about 100.
So it's fine then, that's what you do?
We divide it by something. We divide it by 250 afterwards. When you multiply two polynomials, you get delta square, which is the scaling factor that you use, right? And then we divide it. I'll get to that later. It's there in the workshop. Yeah. It resolves the question. I understood the question. Okay, now we have SIMD encoding, coefficient encoding. Now, this is just the code that I've written how SIMD encoding works, just in case, like if you want to understand internally how this works. So the interesting thing is that you can use these two functions to encode a vector as a SIMD polynomial, like polynomial in the ring. So that, like for example, you get this particular vector, you encode it into a polynomial, or this particular vector encoded into a polynomial. You can use this function. And this function internally calls an FFT operation. That's it. Like this is an FFT operation internally. And I've tried. So over here, let me just execute everything so that it works. Okay. So over here, we're sampling two random real vectors. And then we're encoding it using SIMD encode as A and B polynomials, and then we are performing negative multiplication of the polynomials, that is multiplication in the ring, and then we are checking whether the multiplication of the polynomial in the ring corresponds to element-wise multiplication of the vectors, and that's what you're doing over here. And if you run this particular thing over here, you would see that the precision is 51 bits. So what do I mean by that? So, well, in floating point values, you cannot assert equivalence because there's inherent error in the operation itself. So we sort of check how close the value is. So the higher the precision, this means number of bits after decimal that are like equal, and the error is like 2 to the power minus 51. Okay, so the higher this value is, the better it is for us. Okay, so when you think of vectors, what else do you think? Like when you think of vectors, you can perform element-wise multiplication, subtraction, addition. There's another thing that we think of vectors, like can we rotate vectors? Can we rotate vectors left to right, anti-clockwise or clockwise? And turns out we can do that in this plain text structure as well. So for example, in SIMD encoding, if you have SIMD encoding, like you encoding a vector as a polynomial, turns out you can manipulate this polynomial in a way so that the vector itself is rotated. For example, let's say you have A0, A1, A2, A3, and you encode this particular vector as a polynomial A. You can change this polynomial in such a way that the vector is rotated. So for example, if you want to rotate this particular vector to the left by 1, you can you change this polynomial in a way such that it becomes this. Okay? These are rotations. And the way it works internally is something called substitution operation. Like it just substitutes x with x to the power something, depending on the ring structure. And it is mentioned in the hack compute document that I sort of mentioned before, which you can learn more about the theoretical aspects. But the more important thing to know from a developer's perspective is that you can rotate the plain text with any degree, like anti-clockwise, left, right, whatever that is. Okay, so this sort of goes into, okay, yes, so I've given an explanation over here how it works internally, and this is the implementation of substitution, that we are rotating a ring polynomial by left, 1 or 2. And over here, what I'm going to do is that I'm sampling a random vector, SIMD encoding it, and then I'm rotating it and checking whether it matches the rotation or not. Okay, so I rotated it left by 3, and then I checked whether the rotation matches the element-wise rotation or not, and that's what I'm printing over here, and turns out it works. And infinite, in fact, means that it's exactly the same thing. Okay. Cool. Any questions on the plain text structure? So, what have we covered? We have covered coefficient encoding. We've covered SIMD encoding. We also covered that in SIMD encoding, a polynomial multiplication of the of the plain text corresponds to element-wise multiplication. And in SIMD encoding, you can do something more special. That is, you can rotate the plain text. Okay. These are 4 to 5, like 3 to 4 things that we've covered. Now, when I think of seeking as ciphertexts, so we want to take a plain text and then simply fit it inside the ciphertext so that no one knows what the plain text is. The way we do that is, the way I like to think about it is that you're simply adding the plain text to the ciphertext. And before I sort of tell you anything about how do you encrypt a plain text, a CKS plain text, as that you get a CKS ciphertext, I'd have to introduce to you something called ring learning with errors, which is the hardness assumption of the basis of all the FHE that, like all the FHE schemes that exist at present. Okay, so what is ring learning with errors? Does anyone know lattices? Lattices, learning with errors a bit. So turns out you can and ring learning with errors builds on top of lattices. And the hardness assumption is that okay, so let's say we have Q. What is Q? Think of Q as a very big value, right? In practice, it is, let's say 2 to the power 800, like a very big value. Using this Q, we create a ring of polynomials again, which I will denote as RQ. Okay? And N. What is this ring? It is ZQ mod x to the power n plus 1. Are you familiar with what this is? ZQ, ring of integers, modulus Q, right? So this is ZQ, that means, and this ring consists of all the polynomials of which the coefficients are in this ring but have degree less than n. So previously it was all the polynomials that have coefficients as real numbers, but now we have all the polynomials that have coefficient in this ring. Again, ZQ with degree less than n. Now this is RQN. Now the hardness assumption is that if I sample A randomly from RQ, right? So we are sampling A randomly from RQN, and we are sampling S, which is a sequence, from RQN, with the caveat that the coefficients of S are from ternary distribution. So what is the ternary distribution? Well, it's from this particular set, right? Ternary means 3 values. Okay. So from this particular set, so the coefficients of S are sampled from ternary distribution, and then we sample something called E in the ring RQ1, and the coefficients of E are sampled from Gaussian distribution, or the normal distribution with some sigma. Okay. Now my claim is that if I give you negative A S plus E and A, if I give you this without giving you S and E, you can never find what S is. Okay, this is the hardness assumption that we're making. S is a polynomial in this ring with coefficients from this distribution. Okay, so its coefficients could be 1, -1 or 0. Okay? Randomly. Yeah, randomly. Okay, so if I give you B and A, you can never find what S is. This is known as search variant of RLWE. And there's decisional variant as well, but like we don't care about it right now. Okay? Cool. So this is the hardness assumption that we're making for building CKS. Now, how do you put a CKS plaintext inside an RLWE ciphertext? So let's just say that we have this particular RLWE ciphertext, right? Like we have this hardness assumption. Like you have this secret, I randomly sample this thing, and I get B, and I have A here. How can I put a plaintext inside this thing without having to do a lot of stuff? Well, the way it works is that, let's say I have a message M that is from ring Rn. What is Rn? Rn is the ring. Rn is ring x by n plus 1. Right? So it's the polynomial of ring with coefficients and reals modulus x by n plus 1. So we take message in Rn and we scale it by delta. Delta could be any value. For example, if you take delta as 2 power 40, you will have 40 bits of precision in your operations. So we scale the message by delta and simply add to this. And this gives you a CKS ciphertext. And you would observe that by scaling M, we've clearly avoided the bits of M getting jumbled up with E. Because E is error, it's the useless thing. We don't care about it. So this is a CKS ciphertext. Now if I give you B and A, you cannot find what M is because you do not know what S is. Right? So before, the hardness assumption was that if I give you B and A, you cannot find what S is. Again, you cannot find what S is, and given that you cannot find S, you cannot find what delta M is. Okay? So this is the ciphertext. Now, okay, so we've got this delta M. Any questions? scale, but you just multiply the coefficients of n by delta. And delta is 2 power 40, 2 power 50 that I mentioned before, like your precision values. How much precision you want in your calculations. Okay?
What was the law of data in this? To me, what's the law of data?
What's the role of delta?
The law of data, yeah.
Okay. Yeah. The role of delta is that, you know this error E, right? This error is random. And the hardness assumption wants this error to be there so that you cannot find what S is. We want to avoid the bits of M getting jumbled up with the error. So we scale it. Yeah, we scale it so that it does not get jumbled up with the bits of E. So we scale it by delta. Now this delta is big, like 2 power 40, 2 power 50, 2 power 60.
Yeah, it was just calculating. To me, that it has to be big, but
yeah, so it is just to get jumbled up, it is just to avoid getting jumbled up with E. But okay, fine, what I can do is that I can try to give you an intuition, a better intuition of like why we want to scale it. Okay, let's just try it one more time. Let's just get rid of this mathematical thing. Let's just think of in terms of diagrams.
Can be some proportion distributions of how small are they? Typically less than 1.
6, somewhere like probably 6. The norm of the value, like the magnitude that you can expect to have, is around like 20, 30. That's it. Very small. Very small. Initially, it grows over time as you perform more compute, but initially it's very small. Okay. Okay, think of this box. This is Q. Okay? This is the size of the ciphertext, which is Q. Which is the Q in the RQN. Right? This is the size of the entire box. Now we sample error from a Gaussian distribution, which would have a magnitude of like very small. The point is that if I add error, like if I add message like this over here, simply, then my message would get jumbled up with the error because it is being added, and this error is random. So I want my message to be, I want to avoid my message to get added to this error. So I scale it by delta. So I scale it by delta, which is still big, so that my message is starting from this point. So now this is my message. Okay? Cool. So now, how do we do, so once we have ciphertext of ZK11, like once we know we have a ciphertext, how do we work with that ciphertext? Like how do we perform operations on the ciphertext so that the same operations are performed on the plaintext? Okay? So first is, like, before we do that, I would like you to sort of imagine the decryption structure of the ciphertext. So since ciphertext was B is equal to A S plus E plus delta M, and A was A simply of this. The decryption structure of this is B plus AS. And why is that the case? Well, when you multiply A with S, you cancel this out, and you only get delta M plus E. Right? So when I speak of decryption structure, I'm speaking of this particular equation of B plus AS. Okay? In which case C0 is B and C01 is A.
Is there a limit to how many until error is getting E and
Yes, there's a limit. There's a limit after which, like intuitively when you reason through these things, if you add to ciphertext, the error would get added as well. So there's a limit to which you can perform additions. and when you perform multiplications, the error would get multiplied. So there's also a limit to which you can perform multiplications. Yeah, it does affect, and we do something called bootstrapping operation, which in fact means that we get rid of this error homomorphically. We homomorphically run this decryption structure with encryptions of S to get a ciphertext with reduced error. That is one of the most expensive operations in FHE. But I can get to that afterwards. But first, let's just understand how do different operations on ciphertext work. So we got addition. So once we know this decryption, addition. Well, addition is a simple addition of these ciphertext components. For example, let's say there are two ciphertexts, ciphertext 0, ciphertext 1. Addition is, let's say this is B0, A0, and this is B1, A1. Addition is simple addition of these two values. Okay, you simply add these values up. You get the addition of the ciphertexts. Okay, and the subtraction is simple subtraction of these values. Okay, these are two polynomials, you add them and subtract them. And the reason it works is because if you look at the decryption structure, it gives you addition of the messages, right? But the errors get added as well, and you have increased error, which is why there's a bound to amount of additions that you can do. But the increase is not much. It is like just twice the previous value. And in terms of bits, it's like just 1 bit got increased, right? Now, how do you multiply two ciphertexts? Well, okay, so in order to explain multiplication, I'll have to sort of okay, so for multiplication, let's take two ciphertext, C0 and C1. C0 is equivalent to, let's say, B0 and A0, and C1 is equal to B1, A1. And you know the decryption structure, if you have the secret key, you can get the message back, which is delta M0 plus error and delta M1 plus error. Okay? Right? So we got the decryption structure. This is a ciphertext. How do you multiply two ciphertexts? Well, multiplication is okay. So wait a minute. So we know that this is the decryption structure of these values, right? Because when you multiply S with this, you'd be able to get when you multiply S with A added with B, it is equivalent to M plus E. Same applies for this one. So to multiply to ciphertext, you actually perform tensoring of these components. So you multiply, you tensor these two ciphertext. Now, are you guys familiar with tensoring? Tensoring is simple as this. So you just multiply the cross components, right? So it is tensoring of these two values would be B0 B1 plus, sorry, it would be B0 B1 B0 A1 plus A0 B1, and that should be A0 A1. Okay? So this is the tensoring of these two ciphertexts. And what does that gives us? Well, it gives us the encryption of, well, okay, so tensoring is this, right? So you perform tensoring between these two components, you get this particular thing. Okay? When you tensor two decryption structures, you get the same thing but with S at the end. So if you have secret, if you have access to the secret, you can decrypt this particular ciphertext by itself. So, okay, is that making sense, or am I going too fast? Cool. Okay, so let me try to explain it much better way.
Do you need to keep track of how many times you multiply?
Unfortunately not. Like if it was this way, then yes. But I'll tell you a way to reduce this particular degree afterward. So you multiply two ciphertexts with tensoring, and the decryption structure of a tensor ciphertext is this, with S and S squared. Now, initially, we were working with a degree 1 ciphertext when we think of S as the X of the polynomial. So you only needed the access to the secret to be able to decrypt it. But now we need the access to the secret square to be able to decrypt it. And this is a problem for us because when we multiply the ciphertext again, it will become x to the power 4, x to the power 6, x to the power 16, x to the power, and then so on and so forth. So the increase in the degree will be exponential, which is bad for us. So what we need is a way to go from degree 2 to a degree 1 ciphertext, right? And the way we do that is we homomorphically multiply, like we use FHE itself to do things. We homomorphically multiply this particular term with the encryption of S squared. And this operation is known as relinearization operation, FHE. It's a very simple key switching operation. You can think of this S squared as a different key, and we switch from S squared to S. And we are able to reduce a ciphertext as S squared to S. And the key thing to note in this particular thing is that it is an expensive operation, which is why multiplications are more expensive than additions. Okay? Now, what happens to the message when we multiply? Our message was delta, our message was delta M0 plus E0 and delta M1 plus E1. When we multiply these two things, what do we get? We get delta square M0 M1 and then delta M0 E1 plus delta M1 E0, right? So but instead of this, we wanted multiplication of M0 and M1. That's Hello. Okay. So multiplication gives us multiplication of M0 and M1, but with square of the delta. But this is not what we want. We want delta, right? So what we essentially do is that we divide the entire thing with delta, and we end up getting delta M0 M1 with reduced error because you divide everything by delta. But the error is increased. Also because you multiplied M0 and E1, and the error that is induced depends on the size of M0, because when you multiply a big value with a small value, the error depends on the big value. Like the amount of the resulting value would depend on the big value, hence the error in this case depends on M0. And the important thing to note over here is that multiplication, the noise growth is higher, like the error increases higher than additions. Okay. Now, okay. Cool. So rotations. Well, rotations I would quickly run through them because we're running out of time, and I need to introduce a bit more things. For rotations, it's a simple key switching operation as well. So we rotate the ciphertext by substitution operation. So if your initial ciphertext is this, right? You just substitute x with x to the power k. That's it. That's how you do rotations. You just substitute x with x to the power k. So you perform this substitution operation, and that's it. That would give you message as this, right? Because when the initial decryption structure was C0 plus C1S, which gave you M plus E. When we substituted, it would give you mx per k plus e to the power x plus k. And now we need to switch it back, which is another key switch operation. Okay, so it gives you encryption under S. When you rotate it, it gives you encryption under this, and now you key switch back. So you multiply this with this homomorphically to get an encryption under S. This is another key switch operation that you do, and it is also expensive, but not as expensive as multiplication. Okay. Cool. So now I've told you that we've got CKK ciphertext, and this ciphertext allow you to perform multiplications, addition, subtraction, and if you encode the the plain text as a vector in SIMD format, then you can perform rotations as well, because you can perform element-wise operations in SIMD format. So what we're going to do today is first let's try to build a very small application using it by just leveraging the plain text structure of the CKKS. So just leveraging the CKKS plain text, and then we'll try to homomorphically figure out how to evaluate a CNN using it. Okay, if you're familiar with CNNs, communication neural networks. Okay, so any doubts? Because now we are moving from this plain text thing to application stuff.
So when you are multiplying and linearizing, is that something that you can multiply many times in linearized data? Can you accumulate?
You can accumulate, but in practice no one prefers that for some reason. Yeah, because it is an exponential growth. Yeah, but you can do that for sure. Yeah. Cool. So let's just say that we want to build a rating application, right? Like we want to make sure that you have two users, and you want to match make these users based on their expenditure history. Like how do they spend? So let's just say that how would we build such an application? So usually the way we would build an application is that we would categorize their expenditure history into categories. Like, for example, how much they spend on clothes, how much they spend on flights, food, and sports. And then we'll try to figure out how similar these particular distributions are, right? Like how similar this expenditure history is, okay? That's how you find similarity between two expenditure histories. And the way usually you would do that is by evaluating something called cosine distance. So what is cosine distance? You simply take the distribution, calculate the inner product, and divide it by the norm. And what is norm? Norm is like any L2 norm, if you're familiar with norms. Just like if it is L2 norm, it is like addition of the squares of the values and a square root of that. That's a norm. That's an L2 norm. So the way you calculate cosine distance is that you take these distributions, calculate the inner product, divide by the norm. Now you would notice that this can be translated as to a simple inner product if you make this observation, right? If you rewrite this as this, then it is a simple inner product. So it turns out to calculate a cosine distance between two distributions, the only thing that you care about is evaluating this inner product homomorphically. Okay? So how do you do it? So there's a naive way that exists, but I'll skip the naive way for today because I've given an explanation here and you can look at it afterwards. I would want to tell you a way in which you can leverage the plain text of CKKS such that you can perform an inner product with a single multiplication and a bunch of rotations. Okay? And the way that works is this. Okay. So we have two distributions. Let's say this is me. This is my distribution of 100, 120, 140, 150. And this is someone else's distribution, right? Some unknown person. Another distribution of 500, and so on and so forth. we want to find the cosine distance homomorphically of this. The way it would work is that we would encrypt both of these as SIMD plaintexts. So as a vector, as inside the sticky case plaintext, right? Now when we encrypt this into polynomials, let's say, okay, let's just think of this as small j, right? Just better to note. And then when we encode it using SIMD encoding, we get a polynomial j, right? And now when we get another polynomial called a. When we multiply these two polynomials, we know that it would be element-wise multiplication on these particular vectors because it is encoded as SIMD, right? So first, before we do the inner product, we first encode them as plaintext, SIMD plaintext, and then perform a multiplication, which in fact multiplies these values element-wise. Let's say multiplication of these two values, which is this. Right? These are two distributions, A0, A1, A2, A3, B0, B1, B2, B3. You encode them as SIMD and you multiply them. You get a plain text that encrypts a element-wise multiplication of these values. Okay? Make sense? Okay, now how do we calculate the inner product? So we have the multiplication, we just need to add all these values, right? Inner product is the multiplication and the addition of these values. The way we do that is via rotation. So first we rotate the existing value to the left by 1 and add it to itself. We get this. And then we rotate this by 2, add it to itself, and we get this, which is the addition of all the values. So this is, and if you have like a vector of size n, you can add all the values with logarithmic number of rotations, right? And that's it. So that's what we've done here. We encode the inputs as SIMD plaintexts. We multiply them here once, and then we rotate them repeatedly logarithmic number of times. Log a number of times by doubling the number of rotations that you would do, like number of slots that you would rotate by after every iteration. And then we check whether the cosine function works, and this is what we wanted, and this is what we have. Like, so this is pretty simple. Like, we were able to do this using CKS plaintext. Okay? Any questions? Left 10 minutes, right? Cool. Any questions? Okay, so now I would like to move on to CNNs. How do you work with CNN? So, are you familiar with CNNs? Convolutional neural networks. So you know the normal way CNNs work is that you encrypt the encrypt the inputs of the user. So you do not encrypt. Sorry, you just get the inputs of the user in plain text, and then you evaluate the model. How about evaluating the model on encrypted user inputs? And so what are we going to do today is we're going to evaluate a CNN model with encrypted user inputs instead of having user inputs as plain text. And I'm going to show you how to evaluate this single convolution layer. So okay, so what is a CNN? If you're familiar with it, because CNN is go ahead. Okay. The way I like to think about CNN is it contains a bunch of convolutional layers. A single convolutional layer is something like this. You got input channels, you got kernels, you got output channels. Each kernel operates with a particular input channel, something called convolution operation, which is a simple inner product between the area that it covers, and produces an output for the output channel, right? So this particular thing is a single convolution layer, and then after which you perform activation function on the output elements. And now you can stack multiple of these convolution layer on top of each other to evaluate a CNN. Right? A CNN is just a collection of these convolution layers. Okay, so if I can show you that how to evaluate this particular layer with encrypted input channels, then you can, like if I can give you a circuit for this, then you can stack this circuit on top of each other to evaluate the entire CNN architecture yourself. Like for multiple, like a CNN architecture of like something like ResNet 20 or ResNet 50 or something like that. Okay? We just got 7 minutes left, so I would like to I would like to skip the boring parts honestly, and move on to the interesting part. Okay, so over here what I've done is that so turns out you can do this convolution operation that I was mentioning before, this particular convolution operation. Right, so you have input channels, you have kernels. Turns out, now when I say batch convolution, what I mean is that we perform a convolution operation for all the kernels for a specific output channel. Right, so you've got input channels, kernels for those input channels for a particular output channel, and a batch convolution is that you perform convolution for a specific output channel. Right, and turns out using CKKS you can do this using a single negacyclic multiplication. So you can encode input channels inside a CKKS plain text at certain indices such that a multiplication, a negacyclic multiplication would give you a convolution operation. Right? So it turns out a single negacyclic multiplication can give you the output channels. Now, over here I've showed how to do that, but I think this is the boring part, which is why I would like to move on to the next thing, which is the more interesting part, which is how do you evaluate the ReLU activation function after you're done with this convolution, and after you've got this convolution output, how do you evaluate the activation function? Now, another interesting part before this is that for the convolution operation, okay, so yes, are you familiar with ReLU functions? ReLU activation function? Okay, so once we have done this convolution, the second part in convolution layer is to evaluate the activation function of the output elements, right? And the caveat in this case is that ReLU is a non-linear function. Like what is ReLU? ReLU is this: maximum of 0 and x. Right? This is ReLU function. This is a non-linear function. How do you evaluate a non-linear function when you only have access to multiplication, addition and subtraction? Right? How do you do that? Well, you just give up on evaluating that particular function accurately. The way you do that, you use something called polynomial approximation. You try to approximate the ReLU function using a polynomial. And the way we do that today is by first approximating the sine function and then using the sine function to build the ReLU function. Okay? So if I give you a sine function, sine x, that returns 1 if x is positive and returns negative 1 when the x is negative. And when x is 0, it returns 1. Okay? So if I give you the sine function, then you can build the ReLU function as x plus x times sine by 2. Because when x is positive, this will return 1. So it becomes 2x and it becomes x again. When x is negative, this will return negative 1 and this thing cancels out. Right? So you can build a ReLU function using the sine function. And now we have to figure out how to approximate the sine function. Now there are several ways to approximate the sine function, and I'm just using a simple. Okay, let me just. Yeah, so for today, we'll be using this particular sign function approximation. This probably is moreover given most of the time.
Is there a specific reason you want to use zero for the?
Yeah, because most of the CNNs use rel in practice.
Yeah, but actually you can use like the approximation.
You can replace the acquisition function with a polynomial approximation as well, like a polynomial function, but people are not willing to spend millions of dollars to retrain their model. Yeah, so if you can do that for sure, you would have faster latency. But this also highlights an inherent trade-off in ZK11, right? Because if you want higher accuracy, then you would want higher approximation. But intuitively, higher approximation would require higher degree polynomial, and higher degree polynomial would require a lot of multiplications, hence higher latency, right? But if you do not want higher accuracy, you can trade off the degree with the accuracy, and that now if you want lesser accuracy, then a lower degree polynomial would do, but turns out like people wouldn't be comfortable with lower accuracy. So this is a hidden trade-off that exists in ZK11. And the most painful part in evaluating CNNs homomorphically using FHE is this thing, like activation functions. How do you perform a non-linear thing using a linear only multiplication and additions? So we will be using this particular function today, and the main part to note the main thing to note in this function is that this particular function only works over the range of -1 and 1, and has an accuracy of 2 to the power -10. Now you can change it to the power minus alpha. It could have any accuracy. Like when I say 2 to the power -10 accuracy, it is like 10 bits of accuracy. And you can sort of change the function to get any bit of accuracy as you want. But if you want more accuracy, the degree of the polynomial would increase. So higher, like you have to perform more operations. If you want less accuracy, the degree would decrease. And in practice, you're sort of like trading off these things. A higher degree or lower degree, depending on how much latency you want, how much accuracy you want. But the main point here is that you only have access to like -1 and 1 input domain. Like the input range is -1 to 1. But in practice, the ReLU function, the CNNs does not guarantee you that the input would be -1 to 1, right? So how do we do that? How do we increase the input range of this thing? Well, the solution is pretty trivial. We just scale it. So instead of using this function directly, just 2 minutes. Instead of evaluating this function directly, we first experimentally determine what the input range is. Like if experimentally determine with a lot of tests, like what the input range is, and we set -b to b as the input range, right? Now we scale this particular input by we scale the input by b so that the input is in the range of -1 to 1, and then we scale it back. Okay, so we take the input, scale it by b, and then we scale it back. So we are able to get the input range in -1 to 1 and then scale it back. And now the problem with this thing is that now the error that is introduced by this, which is of 2 to the power -10, is also scaled. It becomes b into the power -10, and that's what we're trying to do over here. So this is the sine function, and this is the ReLU function built on the sine function. You can see that first I'm scaling it down by b here, and then I'm evaluating the sine function, and then the ReLU function, which is x plus x times sine, and then I'm scaling it back here. Now you would notice that for 20, like the range of -20 to 20, if b is 20, the precision is 7 bits. But if I increase the bound to, let's say, 50, the precision is 12, but it should decrease. So. There's something wrong here, but the precision should decrease. But yeah, as the bound increases, the precision should decrease. That's